Hello everyone, I'm Mohammad Yusuf Azimi, a PhD candidate at the Computer Science Department of Sabancı University. I will briefly present our work on model-based test adaptation for smart TVs. This research has been done in collaboration with Arçelik under ETIA project and is partially funded and supported by Unit Information Technologies and the Scientific and Technological Research Council of Turkey. In this work, we propose an approach to the test adaptation of smart TVs produced by Arçelik. Arçelik is the fourth largest home appliances manufacturer in Europe. It operates in 100 different countries under 10 different brand names, such as Beko and Grundig. Arçelik maintains hundreds of test cases capturing decades of experience to test their smart TVs. Arçelik have developed some methods to ease the adaptation of test cases. For instance, the commonalities between the test cases are put into modules to ease the adaptation. However, many existing test cases break in the presence of a change in the user interface of the software. And typically, the user interface of the software changes in every software update. In this context, a test case is basically expressed as a sequence of low-level remote controller actions like up, down, left, right, OK, and so on. These test cases are automatically executed. And as we have observed, even small changes in the UI of the software results in breaking many of the existing test cases. Shown here is a screen capture of the main menu of a smart TV that is produced by Arçelik. For simplicity purposes, imagine that there is a test case that opens the settings. And as mentioned earlier, since the test cases are expressed as a sequence of low-level remote controller actions, this test case would simply be down, right, 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 and then OK. Shown here is another screen capture of the main menu of the same smart TV with a relatively newer version. As you can see, the user interface has changed a lot compared to the older version. The test case that was used to open the settings in the previous version has suddenly become up, right, right, and OK in this version of the software. Arçelik manually adapts the test cases, which is quite time-consuming, keeping in mind that it has to be done repeatedly every time the user interface of the software changes. And it is proven that manually adapting test cases are error-prone, costly, and tedious. Besides other challenges of adaptation, adaptation in this context has its own challenges. I will mention some of them here. First, limited support is provided by the underlying platform. Unlike web and mobile, in this context, it may not necessarily provide us with the object models. For instance, in the case of a web application, document object model or the DOM of a web page can easily be taken. This DOM can be really useful in the process of adaptation. We cannot expect the same support in the context of consumer electronics. Second, the effect of the UI changes is profound. We have observed that even slight changes result in profound changes in the sequence of actions that needs to be performed. Existing approaches often assume that changes are within the same individual screens, and changes do not change the sequence of screens to be visited. And when this is not met, they randomly guess to find their way, which is quite inefficient. And lastly, the statefulness of the interactions. This means that the same actions on the same UI element can behave differently depending on the state of the system. For example, pressing back button may result in different outcomes as it typically takes the user to the preceding menu item visited. To conduct our experiments and to evaluate our approach, we have a setup that contains two specialized hardware devices. Shown here is a sample setup that we have in the software engineering lab at Sabancı University. First, we have a manageable remote controller called Tira. Tira is basically a programmatically manageable remote controller. This device enables us to send commands from the PC to the smart TV. Second, we have a USB connected capture device. This device is used to capture the frames from the smart TV and send them to the computer, which will be analyzed. As mentioned earlier, in this context, it may not provide us with the object model. Thus, we extract all the necessary information from the screen images themselves by using image processing techniques. Arçelik, as the fourth largest home appliances manufacturer in Europe, suffers from the fragility of their test cases. Therefore, to tackle this problem, in this work, we propose an approach of test adaptation in which, given a test suite known to be working on an older version of the system, it automatically adapts that test suite into the newer version of the system. Although in this work, we specifically focus on smart TVs produced by a single company, our approach can be readily used on any consumer electronics with a screen-based user interface. This is because our approach is a completely black box approach. In the proposed approach, we operate by interpreting the images of user interfaces to interact with the system. At a very high level, our approach consists of these two steps. The first one is a model discovery step, and the second one is a test adaptation step. In this phase, we discover a model for both the old and the new version of the system. Model discovery is done by an automated crawler that we have developed, which opportunistically crawls the system. We call it opportunistic in the sense that it tries to do all the possible remote controller actions on all the UI elements in the system. In addition to that, we also steer the crawling to the portion of the system that's not yet discovered. In our approach, a model is basically a non-deterministic finite state machine. Each state represents the currently selected item on the screen, and each transition labeled by a remote controller command represents a change in the state. The reason behind a model-based approach is to reduce the guesswork and to do the adaptation in an efficient way, especially when there is a significant change in the UI of the software and the order of screens to be visited is changed. Given a test case T known to be working on the older version of the system, to adapt it to the newer version of the system, we do the following steps. First, since T is just a sequence of low-level remote controller actions, it may not be very useful originally. So we first execute the test case on the old system and trace the path that is traversed by that test case. Once we know the path that is traversed by that test case, we find semantically similar states corresponding to each state in the new model. We find a path that traverses those corresponding states in the new system dynamically and in a feedback-driven way. We say dynamically and in a feedback-driven way because we execute the commands on the smart TV itself. Check if you're at the expected state or not, and decide based on that. We are currently evaluating our work by adapting real test cases being used by Arçelik on different versions of a smart TV. Our initial findings are quite promising, and it encourages us to carry out further research and continue working in this field. Our ultimate goal is to develop sophisticated approaches to adapt test cases not only for smart TVs, but for all consumer electronics with a screen-based user interface. Now let me show you a small demo of what we are actually doing. Discovery of the models are done by an automated crawler that we have developed. To discover a model, we start our crawler, which crawls the smart TV in an automated manner. I have already started the crawler in debug mode to show you how it discovers a model and what exactly a model is. The reason that we are discovering a model is to reduce the guesswork and do the adaptation in an efficient way. This picture here shows the screen, the current screen of the smart TV. And since I'm at the beginning of the crawling, I only have one state in my model, which is my initial state. There are some information that we store regarding a state, one of which is the textual information of the state, which is extracted by OCR. The next thing that we store is the selected area image of the state. And we also store the whole screen image as well. It's important to note that the crawling is done in an opportunistic way, meaning that for each state, it does all the possible actions at least once. Once I proceed, the crawler will decide on a remote controller action to be performed. It actually does the action and save the resulted state in the model if it's not already there. So as you can see, this state, which is live TV, was not in my model, so I added it to my model. And I also added a transition from my previous state to the current state, which is right here. Once I proceed again, it will again decide on an action and it will store the resulted state in my model if it's not already there. In this case, Application Center was not in my model, so I added it to my model. And I also added another transition, which is from the second state to the third state, which is from the live TV to the Application Center. Now that we have our models discovered, I will briefly show adaptation of a test case. As mentioned earlier, test cases are simply a sequence of low-level remote controller actions. Here is a sequence of actions that resets the smart TV. We first execute this test case in the old version and trace the path traversed. Executing a test case means to do all the remote controller actions in that test case. For instance, in this specific test case, we do these actions from top to bottom. Let's execute this in the old version. These are the states that were visited by that test case. Now that we know which states were visited in the old model, I can find similar corresponding states in the new model. Once I know which states needs to be visited in the new model, I can find a path that visits those states. There can be two strategies here. First, my goal can be to reach the final state without caring about the middle steps. Or it can be the case that I visit all these states here. Since in this test case, the goal is to reset the TV, meaning that to reach the final state, so we will follow the first strategy. Now we know that we have to find a path to some specific state, so we can use our model to find that path. We do this dynamically and in a feedback-driven manner, meaning that on each step, we figure out which state we are in and which action has to be performed that get us one step closer to the target. Let me show you what exactly it means. This here is the current screen of the smart TV. I need to figure out which state I'm in and ask my model to give me an action that gets me closer to the target. In this case, my model will tell me to go up. Then again, I figure out the current state that I'm in, and I ask my model again to give me an action, which in this case, it will tell me to go right. I do this until I reach the final target. The sequence of remote controller actions that was used to lead me to the target state is saved as an adapted test case, which is shown here. In other words, this sequence of remote controller actions will reset the new version of the smart TV.